Google search handles over 3.5 billion searches per day. That's 40,000 queries per second. What happens when a sudden surge in traffic overloads your database? Today, we'll explore caching strategies to handle this massive scale and prevent system meltdown. By the end of this video, you'll know how to choose the right caching strategy for any system design interview.
First, let's define the scope. Functionally, we need to cache frequently accessed data to reduce database load and improve response times. Non-functional requirements include low latency, sub 50 milliseconds for cache hits, high availability, cache should be resilient to failures, and eventual consistency. Stale data is acceptable for short periods. A clarifying question: what type of data are we caching? Is it read-heavy or write-heavy? This will influence our choice of caching strategy.
Let's estimate our caching needs. Assume 10 million daily active users, each performing 10 read operations per day. That's 100 million reads per day, or roughly 1150 queries per second, QPS. If each cached item is 1 KB, and we want to cache 20% of the data, we'll need approximately 200 gigabytes of cache storage. Bandwidth? With 1150 QPS and 1 KB per item, we need 1.15 megabytes per second of bandwidth.
Now let's design the high-level architecture. We'll use a cache aside pattern. Clients first check the cache, read us. On a cache hit, data is returned directly. On a cache miss, the data is fetched from the database, PostgreSQL, populated into the cache, and then returned to the client. We could also consider a read-through cache, where the cache itself is responsible for fetching data from the database, but cache aside gives us more control over cache population. Here's where most engineers make a critical mistake. They only consider the happy path. What happens when the database is updated?
Let's dive deeper into core caching logic. We need to consider TTL, time to live, and LRU, least recently used, eviction. TTL determines how long a cached item remains valid. A short TTL ensures data freshness but increases database load. A long TTL reduces database load but risks serving stale data. LRU is an eviction policy that removes the least recently accessed items when the cache is full. It's typically implemented using a doubly linked list and a hash map for O1 access. Now, your interviewer will push back. Why not use LFU, least frequently used, instead? LRU adapt better to changing access patterns. LFU can get stuck with infrequently accessed but initially popular items. The mistake most candidates make is not considering the trade-offs. We gain freshness with short TTL but sacrifice cache hit rate. We gain high hit rate with large cache but sacrifice cost.
Let's define the data model for our cache. We'll use Redis as our cache store. The schema is simple: key, string, and value, JSON. The key could be the user ID or product ID. The value is the cached data itself. We'll add audit fields like created at and updated at to track cache entry creation and modification times. For data lineage, we can include a source table field to indicate the origin of the cached data. Pause here. What's missing from the schema? Consider adding a version field to handle cache invalidation during database updates.
To handle the estimated 1150 QPS, we'll need to scale our caching layer. We'll use Redis replication for high availability. If the primary Redis instance fails, a replica will take over. For even greater scale, we can shard our cache across multiple Redis instances using consistent hashing. Now let's talk about write-through versus write-back caches. With write-through, data is written to both the cache and the database simultaneously. This ensures strong consistency but increases write latency. With write-back, data is written only to the cache, and the database is updated asynchronously. This improves write performance but risks data loss if the cache fails. This brings us to a crucial challenge, the cache stampede problem. This occurs when a large number of requests hit the cache simultaneously after a cache expiration. To mitigate this, we can use probabilistic early expiration, where we add a small random jitter to the TTL of each cached item.
For reliability, we need to monitor our cache hit rate, latency, and error rate. We'll set up alerts to notify us of any anomalies. To ensure cache consistency, we need a robust cache invalidation strategy. When data in the database is updated, we need to invalidate the corresponding cache entry. This can be done using a message queue, Kafka, to notify the caching service of the update. If the cache service fails, we'll use a circuit breaker pattern to prevent cascading failures. In summary, we've designed a scalable and reliable caching system using cache-aside, TTL, LRU, and Redis. The key trade-offs are consistency versus latency and cost versus performance. Potential bottlenecks include cache stampedes and cache invalidation. Next steps would be to implement more sophisticated cache eviction policies and explore distributed caching solutions. Remember, the best caching strategy depends on your specific use case and requirements.
Join our community of engineers mastering software engineering, algorithms, and technical skills. Subscribe to stay connected and never miss a tutorial.